Hello and welcome. In this lecture we are going to cover the direct synthesis method for obtaining controller algorithms and tuning parameters. So let's look at a feedback loop. The basic idea behind the direct synthesis method is, let us say y set point goes as a step. Now I say that okay, in response to this step I want my controller the system output y to have a desired shape. Goes from, yeah. So if you look at the complete system, then y by y set point is actually GCGP divided by 1 plus GCGP. And when I say for a given y set point I want a particular, for example what I have drawn here is a first order lag simple exponential kind of response, that corresponds to specifying the closed loop transfer function. So when I say that y should respond as a first order lag of a certain speed, my specification could be very slow, it could be very aggressive. These are all potential specifications, but basically what I'm trying to say is my y should rise as a first order lag with a certain speed, and let lambda be the parameter that characterizes that speed of response of that first order lag, the time constant corresponding to that first order lag. This specification is equivalent to specifying the closed loop transfer function, because I have specified y and y sp is 1 by s, so it's equivalent to specifying the transfer function. Now if you look at the transfer function, this is specified, this is known, so I can now calculate GC, and you can see divide numerator and denominator by GP. Let's not do that. So we'll take G CL times 1 plus GCGP is equal to GCGP and so if I keep the GC terms on one side and take everything else on the right hand side, GC times GP minus GP G closed loop S is equal to G closed loop, and this implies that GC should be G closed loop, which has been specified by the user, 1 by GP times 1 minus G closed loop, which has been specified by the user. So this is how you back calculate what the controller equation should be for a specified closed loop transfer function. So the basic idea is specify unit step servo response transfer function for a given process transfer function, and you back calculate the controller equation from the feedback loop transfer function equation, which is what we have done. And we've used this closed loop transfer function equation in which GP and this are known to calculate GC, and so GC is back calculated as shown here. And now let's just apply this technique to some very simple transfer functions. The simplest transfer function, let's take an integrator, a pure integrator. So if you have a pure integrator, then G controller is going to be 1 by GP, so 1 by K by S. Let's take, I want the transfer function G closed loop spec to be 1 by lambda, a simple first order lag. So what this means is, if my set point goes up as a step, the output goes up as a first order lag to the set point, and lambda is the parameter that characterizes the speed of this rise, exponential rise, first order rise to the set point. So if lambda is taken very small, I'm wanting aggressive control, and if lambda is large, then I'm wanting sluggish control. So if G closed loop specified is 1 by lambda s plus 1, then GC will be 1 by lambda s plus 1 divided by 1 minus 1 by lambda s plus 1, and this guy turns out to be s by k into 1 by lambda s plus 1 minus 1 cancels out, and then the s and s also cancel out, and so you're left with GC is equal to 1 by k lambda. This is a P only controller, a proportional only controller. We know this as a P only controller. So what we have is, for GCL specified as a first order lag, the controller equation turns out to be a proportional controller, a P only controller with gain Kc is equal to 1 by k lambda. And what this is saying is, if I make lambda smaller, if lambda decreases, Kc increases. So lambda is the tuning parameter that is determining how aggressive Kc is going to be. So lambda is my parameter that determines the tuning. That determines the tuning. Okay, so now let's consider a first order lag. So if you look at a first order lag, and again let us say I want my closed loop response to be a first order lag. So if I want it to be a first order lag, not tau bhaiya, lambda, and lambda is the tuning parameter that determines how aggressive control do I want, then GC in this case will turn out to be 1 over k by tau s plus 1 multiplied by G closed loop, which is 1 over lambda s plus 1 divided by 1 minus 1 over lambda s plus 1. And when you do the algebra, this will turn out to be tau s plus 1 into 1 by k divided by lambda s plus 1 minus 1. So that's going to be just lambda s, and this guy turns out to be 1 by k, take tau by lambda common, and so I'll get 1 plus 1 by tau s. You can see this is actually a PI controller with its gain is equal to 1 by k times tau by lambda, and integral time tau I is equal to tau. So a first order lag for the servo response to be a first order lag with time constant lambda, we need to have a PI controller with Kc equal to 1 by k tau by lambda and tau I is equal to tau. Again, notice that as lambda is decreased, that means I want more and more aggressive control, Kc goes up. So if lambda goes down, Kc goes up. So for this chosen G closed loop spec servo transfer function, desired servo transfer function, I get a PI control law, and in this PI control law the controller gain is given by this, and tau I, the integral time, must be the process time constant tau. Okay, let's look at now maybe a second order lag. Yeah, okay, so for a second order lag, again I say, okay, my closed loop response specified should be a first order lag with time constant lambda. In this case, again Gc will turn out to be tau 1s plus 1, oh this guy should be tau 2, sorry, multiplied by tau 2s plus 1 divided by k, that's 1 by gp, multiplied by multiplied by, in the denominator, multiplied by 1 minus GCL spec, which is 1 over lambda s plus 1, and of course here also you have 1 over lambda s plus 1, because the numerator is GCL and denominator is GP times 1 minus GCL. Okay, so this guy turns out to be lambda s plus 1 minus 1, that will be lambda s, it will be tau 1 tau 2 s square 1 by k divided by lambda s plus tau 1 plus tau 2 s plus 1, and we will take one by k remains, we will take lambda out, and we will also take tau 1 plus tau 2 out. So then this term will become 1, this term will become 1 by tau 1 plus tau 2 times 1 by s, and the last term becomes tau 1 tau 2 divided by tau 1 plus tau 2 multiplied by S. You can see this is the PID control law, because we have in the PID control law U is equal to Kc into E plus 1 by tau I integral of E dt plus tau d into dE by dt. Now if everything is presented as a deviation variable, where U is deviation from the initial steady state and E is error from the initial steady state, then the Laplace transforming both sides, we will get G controller, that is equal to G controller for a PID controller is going to be equal to U by E, that's going to be Kc, that's going to be Kc times 1 plus 1 by tau I times S plus tau d times S. Even though this is improper in the sense that numerator order is greater than denominator order, nevertheless, the point is that this GC that we have obtained is of the same form as a PID controller, and therefore we get a PID controller with Kc is equal to 1 by K times tau 1 plus tau 2 by lambda. We get tau I is equal to tau 1 plus tau 2, and we get tau d is equal to tau 1 tau 2 divided by tau 1 plus tau 2. So for a first order desired servo response transfer function, we get a controller that's a PID controller, which can be expressed in a PID standard PID controller form, and in this form we have the controller gain as here, the integral time as the sum of the two process time constants, and the derivative time as noted here. As an exercise, consider a first order lag plus dead time process where theta is the dead time. Now a reasonable specification for the closed loop response, because the process is such that even if you change the input, nothing happens for theta time units. Therefore a reasonable desired closed loop specified closed loop transfer function is this, where again lambda is the tuning parameter that determines the aggressiveness of the controller. Second order plus lag dead time, do the same thing. Here we've got a second, this is tau 2, yeah, copy paste, one mistake made at one location, you copy paste it, it gets copy pasted everywhere. So we have GP, and again we would like G closed loop spec as here, and what you would observe once you do the algebra, that this results in a PI controller and this results in a PID controller, and then you can obtain Kc expressions for Kc, tau I and tau d. By the way, I would like to point out, I would like to point out here that look, if you change lambda, Kc changes, but tau I and tau d remain the same. Okay, that's the point that I wanted to make. And with this we come to the end of this lecture, or we come to a stage where we can summarize what we have learnt. So in summary, the direct synthesis method, when applied to simple process transfer function such as an integrator, a first order lag or a second order lag. It results in the P, PI and PID control algorithms. That's what we've seen. The method gives tuning parameters in terms of the process parameters and lambda, which determines the aggressiveness of the closed loop response. Lambda is a tuning parameter that determines the aggressiveness of control, and because lambda is now the only tuning parameter that is in the hands of the designer, the tuning method is also sometimes referred to as the lambda tuning method. Would like to highlight that we have taken G closed loop servo actually is equal to GCGP divided by 1 plus GCGP. This was the basis of our design. This is the servo transfer function. You could also have G closed loop regulator, which would be GD over 1 plus GCGP. And the point is, since we have done what we have done for the servo transfer function and derived tuning rules from the servo transfer function by forcing the servo transfer function to have a certain form, therefore we expect that the servo response will be as expected. But then, because the controller has not been designed for the regulator response, the regulator response can be sluggish. So the method is tailored towards desired servo response as presented. Regulator response therefore may be quite sluggish. But of course the same thinking mindset can also be applied to this transfer function to derive control laws for good regulator responses, and then one expects good regulator response, but then the servo response may be compromised. Both are possible. With this we come to the end of this lecture. Thank you very much for your kind attention. This was a short and sweet one. The next one that you will see is actually a long one, so please watch the next one with some amount of patience. Once again, thank you very much for your kind attention. Good day and goodbye.